So we're finding the graph of the function corresponding to when the function is equal to 11. So that would be x squared plus y squared minus 6x plus 2y equals 11. Right? What sort of shape is this? A circle, right? Which would be easier to see if we completed the square, right? So I take my x squared minus my 6x, and then completing the square for this guy. What number do I wish I had? 9, because you take the negative 6 divided by 2 to negative 3, then square it. So plus 9. And then plus y squared plus 2y, and then plus that number we want 1 equals 11 plus 9 plus 1, so that we still have an equal sign. We added 9 to both sides, we added 1 to both sides, and so we get x minus 3 squared plus y plus 1 squared equals, what is that, 21? And so then you can write it as x minus 3 squared over the square root of 21 squared plus y plus 1 squared over the square root of 21 squared equals 1. So it's a circle. Where is the center of the circle? Yeah, 3, negative 1. And what is the radius of the circle? Square root of 21. Okay. If I were to try to graph this whole thing in 3 dimensions, what would it look like?
It's a circle with a radius of 21, but it goes to the right 3 times and then down 1.
Okay, so this guy is just one slice of my landscape.
Okay, now.
So it's like if I'm making my landscape and I slice it when z is 11, I get a circle that's off center. Okay. But this is also, I think we talked about things that look like this. Remember we did our shapes, our different shapes thing in the very first, like towards the end of the first of chapter 2. Do you remember what this might look like? It's not a cylinder. What's that? Not a hyperboloid.
Uh,
Not an ellipsoid. What? Nope. You almost had it there, Alex. It's just a plain old paraboloid. So imagine a parabola where so let's add 10. So imagine a parabola that's so if you go down, if you go over x positive 3x, positive 1y, and then you go down 10, I think. And then you have this parabola that goes, it's like a parabola in regards to the x and z, and it's a parabola in regards to, so that y and z, and it's a parabola in regards to x and z. So it's like a parabolic like hole that you're in. where it's all nice and fine when you're at the very center, but as you get closer to the edges, it gets steeper and steeper. Okay? So it's like this parabola it's like a parabola that has circle symmetry. Okay? And so we call things like that paraboloids. Okay? Everyone good with that? The ability to try, I know it's hard at first to try to visualize these. The more you're able to visualize these, the easier things get later on. Okay? So it's worth trying. It's worth trying. Okay? So let's do another one. Now let's do this one. F of xy equals sine of x times cosine y. Okay? So a vertical trace, instead of doing so the things we were doing before were like particular altitudes, like the topographical map. Now I'm going to do like slices of this landscape. So if I had this landscape, it's over the XY plane, and my function is describing the height, then what are like if you walk the path of x equals negative pi over 4, what does it look like? So for these, you basically like to hold x to y constant is to plug it in. Okay? So you take this function. So for this guy, you say f of negative pi over 4 comma y is going to be, well, what's sine of negative pi over 4? Negative root 2 over 2. So negative root 2 over 2 cosine of y. So it's a cosine function that's negative, so the opposite, and it's scaled a little bit, so not full cosine. Okay. What about when f of 0y? What's that guy going to be? What's it going to be? If I just plug in 0 for x, what do I get? 0, because 0 times anything is 0. So sine of 0 is 0, and so then it doesn't matter what cosine y is, it's 0. Okay? So when x is 0, it's a constant line at 0. Okay? What about when I when I walk along the positive pi over 4? What's that going to be? Yeah, cosine of y. All right? Now let's try these guys. So f of x, negative pi over 4. If I plug in a negative pi over 4 for y, what do I get? Not negative, but positive square root of 2 over 2 sine of x. Okay? And f of x comma 0, what's that going to be? Sine of x. Because cosine of 0 is 1. And then f of x positive pi over 4, this can also be square root of 2 over 2 sine of x. Has anyone figured out what this thing might look like? I'm going to do my best. So um, along the line x equals 0, it's 0. So it's just like it's there. Now when x was wait. No, x equals 0 means we're along the y-axis. Sorry. Can I undo? Yeah. Let me just Control Z that guy. I just need to erase it. Okay. Yeah. All right. When x is 0, then we're at that guy. All right. So when x is, say, negative pi over 4, so let's say that mark is negative pi over 4 x's. Then we have like a negative cosine function. So like kind of along this line here, it's going like that. Okay. Whereas over here in the positive pi over 4, we have a positive cosine function. So it's starting above that line. And then I'm not trying very hard to make my trig function work out well. Okay. And so then over here on when y is 0, I have a sine of x function. So it's going like, okay. Yeah. But it turns out like if I'd gone all the way to pi over 2, I would have gotten like that it's 0 there. It's a straight line there. And negative pi over 2, it's see that guy is there. Also 0 there. Okay. Do I have another space? No, I didn't. Okay, so what does this look like? Hey, have you guys ever had those like mattress pads where it's like squares and there's like that alternate between being above or below? It's like that. So like in some squares, so if you look in some squares, it's bulging up as a trig function, and other squares it's bulging down. So it's like imagine a checkerboard, and you push in all the black spots and pull up all the red spots, but they're kind of curved up. But they stay like all at 0 on the edges. Okay? Let's see if Desmos can do this. I don't know how good this thing is. We'll find out. So Z equals sine X cosine Y. What is it in like? There we go. Okay. So it's like in these squares it's below, and these squares it's above. So it's like one of those mattress pads. Yeah. You guys must be hungry. All right. Yeah. All right. Now, when you do level surface for when you hold one variable constant, when you've got 3 inputs, so notice that like when I have 2 inputs, then like graphing everything is a landscape. But then if I hold something constant, I just get a regular like graph in 2 dimensions, right? So similarly, if you try to graph a function like this, try to graph a function like this, you've got 3 inputs and 1 output, so you need 4 dimensions to graph it, right? So make one of them time and it's a movie. So 3-dimensional landscape movie. Or you can hold one thing constant and you get a surface in 3-dimensional space. Okay? So for instance, say you've got this guy right here. Then what are the surfaces correspond to like if it when it's equal to 0, 1, 2, 3? Okay. So if you hold like when you set like for the zero, then we're talking when f of x, y, z equals 0, which is when 4x squared plus 9y squared minus z squared equals 0. What sort of thing is that? That is one of the things we learned about when we were talking about two-dimensional surfaces in three-dimensional space. Is that what it was called?
Yeah.
Yeah? All right. Yeah. So it's elliptic cone. So it's basically an hourglass, right? It's basically an hourglass going in which direction? Z is up and down. It's the negative one, so it's in the Z direction. So it's an hourglass up and down. Okay? Now what if you set it equal to 1? So 4x squared plus 9y squared minus z squared equals 1. Now what do you have? Hyperboloid of one sheet, yeah? Okay. So let's just like skip ahead to the pictures in the book. So basically, you've got like c equals 0, and then c equals 1, and then c equals 2, and then c equals 3. So you've got hyperboloid of like go from an hourglass to hyperboloid of one sheet where it's kind of expanding out. Like, have you ever been to like a children's museum where they have bubbles and you do the big hula hoop and you pull the string and the hula hoop comes up and the bubbles all around you and it starts coming in at you? This is like the opposite. The bubbles coming out.
We should get a science and math department.
I agree. It's so funny.
Noted. All right.
Be good.
So,
This was a huge slide.
all right. So
I remember that.
Yes.
that is all for this section. Let's take a 5-minute break and then we'll do section 4.3.
Yeah. I want to do it. Yeah. You're gonna go?
Like, I won't this year, but I really want to.
Yeah.
Yeah, he said, sure, I will add it. That'd be fire.
Remember when we filled out that sheet for the
You never did, bro. Yeah, for paintball or whatever.
Yeah.
See, everybody was like, tough one.
No, dude, I said paintball.
Yeah, I said paintball. No.
Big top golf guy.
Yeah, we need to go.
I'm when my shoulders hurt when I wake up in the morning.
It's awful. I miss it every time. So I feel like throwing pickup.
I have no aim, it goes like this, but I'll hit it hard. Like, you got an ace, so we were on the sun, and, it was a flag. It was a flag.
Move into the pattern too, right? Red flag. No, not committed to the pattern. No.
I love how it's like. I didn't even notice. And also, what's up with you in purple? You still like it? He
No,
gave you the marker and you just.
No, I don't need the marker. It's like one of the better markers. So I wanted him to have it back.
Oh man. Okay, this is nice. If we could just keep doing that the whole time, I could maybe pass this class.
There was no calculus there.
Yeah.
Mhm. Now we gotta start the calculus. Mm-hmm.
What do you got?
That's what is it?
Oh, she got.
He's so concerned about my grades all the time.
Dude, I have a B minus in this class right now.
Sometimes I just put the sheet right on.
Let's go. Let's go.
23.
Oh, that's not bad. You're okay. I'll leave that right down with there. You said the exam, it's gonna be graded by Wednesday.
Yeah.
So I'll be depressed both ways. This exam, that exam.
Oh, yeah, that's stupid.
And then you said the actuarial science, like calculus part is at the end, right?
Mhm.
The very end. Are we doing anything like, are we taking a final on it? Or,
The last stuff doesn't end up being in the final. The section on Jacobians. We don't do,
say that again?
it's called Jacobians. Yeah, like Jacob, Jacobians. Uh-huh.
It's a fun name. Is it fun then?
Yeah, yeah.
Yeah, no.
Actuaries
That's perfect.
or no?
My college didn't have as much of a program as Grace does. They didn't have any like an actual science professor like we do. Yeah.
Science is kind of like not rare, but not as popular.
Yeah, I mean it's hard. It's always like one of the best jobs in the country, but it's hard to get that there. So, yep.
Yo soy influencer and
All right. Vámonos.
What? Okay, vámonos.
Vámonos.
Let's go.
Yeah.
See.
All right. So section 4.1 was all fun and games, but now we need to start doing some calculus. So first let's start when we've got just two inputs. So if we've got this situation, like an f of x, y, and say we've got z is equal to it, there's several ways to say what the derivative is. So we call this the partial derivative because you're only taking derivative with respect to one of the inputs. Okay, so it's like a d, but curlier. Okay. It's basically when you do, I don't remember what the name of the symbol is, but when I'm creating them in LaTeX, it's slash partial. Which Microsoft Word has some LaTeX in it and some not. Let's double check if they have it. Insert equation. If I do slash partial, yeah, Microsoft Word has it. So if you're in equation mode and go slash partial, it does it. Okay. We don't need to save that. All right. So I just refer to it as the partial symbol. So if you're drawing it, it's best to kind of like you don't have to curl it as much as it is in like print, but if you curl it a little bit, like that guy. Okay? And it has no like a D has that tail and a partial does not. So you start it from the top. So you start it from the top and just go there. All right? Yeah. Okay. So this is the one way to talk about derivatives like as a thing that you apply to a function. Now, when we've got two inputs, we can't say f prime anymore because we don't know which input you're referring to. Okay? So a shorthand is instead of like doing this, a shorthand is just do sub x. And that means the derivative with respect to x. Okay? Or if you've got a z there, like if z is equal to that, you can also just call it zx. Or if we're referring to z, you can say partial z over partial x. Those are all the same thing. Okay? You'll notice that this is my favorite, these two right here. Okay? So every once in a while, when you need to refer to like a derivative of a function that I don't know if it exists or not yet, this is convenient. Okay? So this is good to know this. I'm gonna use mostly this, but this is still good to know. Okay? So, we're gonna take this guy. I want you to find, both partial derivatives. We need to find fx and fy. Actually, I'll do one of them and then you do the other one. Okay? I'll do the easy one and you do the one with the product rule. So, uh, so basically, I'm gonna do fy. I'm gonna do fy. And so basically, if you're doing fy, you treat x like it's a constant. And you only take derivative with respect to y. So if I look at this guy and I think of all x's as constants, then I've got like a scalar constant times e to the power of a scalar times y, right? So when you take the derivative, you multiply, like the chain rule, you multiply by the scalar in here, there. So then that would be the scalar then times like chain rule. Let's do the chain rule backwards. E to the x squared y times x squared because of the chain rule. So it's x cubed e to the x squared y. Okay? Now you guys do fx and realize you need to do the product rule. You check your answers with people around you. So hopefully you got um e to the x squared y plus 2x squared y e to the x squared y. Right?
Wait, where does the y go?
I'm treating the y like a scalar. When I do the chain rule, I multiply by. Let me slow down. All right. So fx equals, I'm going to do the chain rule on like the first term. So the derivative of x is 1 times e to the x squared y. And then I'm going to do x times e to the x squared y. And then chain rule, multiply by the derivative of the inside with respect to x. Derivative of the inside with respect to x is 2 times x times y. Because I'm treating y like a constant. Okay? So then I get e to the x squared y plus 2x squared y e to the x squared y. All right? And then in your homework, they're going to ask you to plug in numbers. So let's plug in 1, 2 to both of these. So fy of 1, 2, plug in 1 for x, 2 for y, you get what? E squared. And then over here, fx of 1, 2. So you get e squared plus 4 e squared. So that's 5 e squared. Everyone good with that? Okay. So now let's do this one. Let's talk about let's do fx and fy. And then at the point 1/2, 1, 1, 2. No comma there, typo. So then we're gonna plug in, that's x, that's y, and this is f of x, y, f of those two guys. So just a reminder, what we're doing is we're finding fx, finding fy, and then we're plugging in fx of 1/2, 1, and fy of 1/2, 1. We're thinking about the graph of the function. The function is 2 inputs and 1 output, so I think you can graph the function in space.
So.
So for fx, there's the only x's are there. These we treat as constants. And so we get negative x. And for fy, treat everything except the y's as constant, and you get negative 2y. So plugging those numbers in, you would get negative 1/2 here. You would get negative 2 here. And so then let's talk about what these numbers mean. First of all, what sort of thing is this? What sort of thing is it?
Parabola.
It's a paraboloid. And this is a downward facing paraboloid, so it's a paraboloid hill. It's an infinite hill. Okay, it's centered at 0, 0. And so if you're standing at 0, 0, you're standing on an infinite paraboloid hill. Okay, so it's a parabola going down any way you walk from 0, 0. And so if we walk over to, we go like 1/2 in the x direction, 1 in the y direction, then these numbers we just found, they describe our slope in 2 different directions. The first, that negative 1/2 is like in this direction, the slope is negative 1/2. In this direction, the slope is negative 1. Okay? And so this is, fx tells me the slope if I'm walking in a positive x direction. Where I was just, my picture of x direction is this way. Well, let's do right hand rule. X is out of the board. So, this is my slope if I'm walking in a positive x direction. And then, this is my slope if I'm walking in a positive y direction. Okay? And then z is up, so it's telling me like the slope going up or down as if I walk in either direction at any point. That make sense? Yeah.
So like, what would be your answer? Like, if this was a question, like, what would be the answer?
The slope in the x direction is negative 1/2. Slope in the
Okay.
y direction is negative 2. Yeah. Good question. Other questions? Okie doke. Now let's say I've got a parallelogram with side lengths A and B and the angle theta. What is the volume of a parallelogram that is like side length A, side length B, angle theta? What is the volume of that? Yes. Volume is A times B times sine theta. Because B is your base and A sine theta would give B your height. Okay? So we can also use this sort of thing for our formulas. Okay? So if I have a formula, say like the volume given side lengths of parallelogram and the angle, then I can talk about the differential, like how the volume changes when those things change. Okay? So I want you guys to find, if this is my volume, let me move my formula up. So volume equals A B sine theta, I want you to find VA, VB, and V theta. Not sure what you're doing, talk to your neighbors. Or raise your hand.
No. But I say no. If I just have one for, yeah. Where you, which one are you signed? That. Yeah. Now there's like worlds. Another nice. Yeah, all things something.
All right, so VA is B sine theta. VB is A sine theta. And V theta is AB cosine theta. Right? So then if I plug in these numbers, A is 10, B is 20, theta is pi over 6, what are all those equal to? Pi over 6 is a unit circle angle. So you can plug that in. So VA of 10, 20 pi over 6 is going to be what, 10? And VB of 10, 20 pi over 6 is going to be 5. And V theta of 10, 20 pi over 6 can equal what? So 200 times square root of 3 over 2. So 100 square root of 3. Right? How do we interpret these numbers? What do they mean? And let's say, what if we gave, I forgot to put units for A and B. What units do you want them to be in? inches? Okay. So then, here, the notation of like the partial is helpful here. So partial V over partial A is the same thing as VA, is 10, and then its units is V's units over A's units. And so it's like 10, it's 10 inches squared per inch change in A. Okay? And then so then like partial V over partial A, that's 5 inches squared for every inch change in A, and V dV d theta is going to be 100 square root of 3 square inches per radian. Okay? So what do these numbers mean? They mean like where your parallelogram is right there, with A being 10, B 20, theta being 5 or 6, is like changing a little bit of A, increasing A by a little bit would be like multiplying the volume 10 times that small change. Okay? And like for every little bit of A you increase it, you're increasing it 10 times that little bit of the volume. And for every bit, this is the B. That's why it looks weird. Okay. And then every little bit you increase B, every little bit you increase B, the volume's increasing by 5 inches squared for every little bit of inch you increase B. Okay? And then for every little bit you increase theta, the volume is increasing by like 100 times square root of 3. For every little bit of radian you increase it, the volume is increasing by 100 square root of 3. Okay? Times that little bit of radian. Okay? So this is great for when you've got lots of formulas that describe things and you want to say like, how would changing this one little input change the output? Okay? Let's see, what was I planning to do here? Maybe let's find all the first order partial derivatives. Find fx, find fy, and find fz. As you're working on these, feel free to compare answers with people around you. Make sure you're doing the product rule, you do FZ.
And.
All right, I'm gonna do it up here. So there's only one x in there, which is nice. So we do x is on the inside of a sine, so we get a cosine of xy squared plus 2z. And then the chain rule says then multiply by y squared. So simplify it, it'll be z y squared cosine of xy squared plus 2z. Everyone good with that? All right, then if we do fy, the same thing. We're doing the chain rule. Y is on the inside of a sine, so z cosine of xy squared plus 2z. And then the chain rule, if y is my variable, would be 2xy. So that would be 2xyz cosine of xy squared plus 2z. Okay, and then for fz, chain rule. So the derivative of z is 1 times sine of xy squared plus 2z plus z times derivative of the sine, and I get cosine of xy squared plus 2z times chain rule 2. Got to end my parenthesis. So maybe simplify that guy. Sine of xy squared plus 2z plus 2z cosine of xy squared plus 2. All right. Everyone good with that? Okay. Now I can take second derivatives. Say I take the derivative with respect to x of this guy, you write it like this. Partial squared f partial x squared. Or fxx. Okay, similar like when we did f double prime. F double prime meant second derivative. So like fxx means the second derivative with respect to x. Okay, I can mix derivatives. So I can take the derivative of f with respect to y and then with respect to x. Okay, and I'll write it like this, where I had f, I took its y derivative and then its x derivative. Sorry, I'm a frog in my throat. There's a nice theorem that says the order doesn't matter. When we're taking derivatives, the order, if we take it with respect to x and then y, or y and then x, it's the same thing. Everyone good with that? So again, these guys are going to be my favorite notations, but every once in a while, I need to use this notation. It's nifty for if we have actual units involved or want to talk about question.
There's not a.
Oh, there's also FYY. Yeah, same thing.
So it's just if we take respect of x, then we do the derivative of y.
Yeah. Okay. You ready for the next example then? All right. So let's find all first and second order partial derivatives. So this is going to take a little bit of time. So we need to find fx, fy, fz. We need to find the mixed second order, so like fxy, fyz, fzx, and we need to find the second order of same variable, so fxx, fyy, and fzz. 9 things. We can do it. I believe in you guys. While you're working that, I'm gonna go get some water from my throat.
Why? No. It's just amazing. Yeah.
I do remember that.
Seen that? No. Oh my gosh.
So, send me.
Let me. So. I know a lot of those you have to do that. It's not. Yeah, for the two. Oh, I understand. Because it's like, yeah, but yeah. Huh? Phoenix. It's no, I had to go to that.
Does everyone check their answers with people around them?
There's no Z, no, there's not two. There's literally no.
Okay, yeah, that's. It's like an intro.
Who's unknown though?
Of the original.
Yeah.
Physics
Wait,
one
what?
doesn't get like.
I'm not, is it?
Wait,
no, I'm not.
All right,
Yeah.
let's get started. So fx is going to be y e to the x plus natural log of z. All right. Fy is just going to be e to the x, and fz is going to be fz would be x over z. Okay. So then if I'm finding f xy, I could start here and take the y derivative, or I can start here and take the x derivative. Either way, I get e to the x. All right. F y z. I could start here and take the z derivative and get 0, or I can start here and take the y derivative and get 0. They're both 0. F x z. I could start here and take the z derivative and get 1 over z, or I can start here and take the x derivative and get 1 over z. Yeah.
So you take the derivative of those separately and multiply them? Or how does that work?
No, you take the derivative of one and then derivative of the other.
Yeah.
So to get here, I could start from here and take the z derivative and get here. And then the x derivative and get here.
Oh, so you take the derivative of the original equation, like of x. and
Yeah.
then You take the derivative of the x equation of
Yeah.
z?
Yeah.
Oh, okay.
Yeah, all right. Or I could have done here and derivative of z to get there. Okay. Now, f xx is still going to be it's just going to be y times e to the x. Fyy is going to be 0, and fzz is going to be negative x over z squared. Any questions about any of that? Okay. All right. Let's go back to this guy. Let's find all the points where f of x equals f of y. think I had the comment there accidentally again. Excuse me.
Oh, why? Equals that more.
All right, so fx is negative x, fy is negative 2y. Excuse me. So the places where they're equal would be when negative x equals negative 2y, which then would be like, let's take the y over here, divide both sides by negative 1/2, and I get x over 2. So it's a line, right? So if you're looking down on this paraboloid hill, it's the x's go, it's like that. And so when y equals x like that, then you're moving perpendicular to the topographical lines, because the x component and the y, your slope in this way and that way are the same. So if I'm hiking up the parabolic hill this way, then like my x, it's the slope in this direction and this direction is the same. So I walk up, and when I start walking down, and the slope is the same. Sound good? All right. I think that might have been it. So now I left about a lot of blank spots so that we could do some review for the exam on Wednesday. Okay? So I'm going to combine a couple exam things. So let's say I have a projectile. Let's say I fire it from, let's say I took some of my golfing stuff on top of McLean, and from the roof of McLean, I hit a golf ball. And so I hit it. What's a good speed for a golf ball being hit by a club? Is that 100 miles an hour? With the driver? Okay. So then let's say let me give it to you in feet per second so we don't have to do that thing. So let's say I hit a golf ball at 120 feet per second. And then I hit it with an upward angle of, say, let's do pi over 6, because I mean that's a little bit ridiculous as a golf thing, but uh it's it's nice angle for our math. All right. And then how many feet high do you think the roof of McLean is?
Well, are you, where you at?
Let's say the ground around McLean is 0. How high is the roof of McLean? Let's say I'm standing like,
Are you on the steeple? In the steeple?
not on the steeple, just like the top of the roof. 40 feet? 50? Let's go 50. It's 50 feet up. Give me the formula for my projectile. And tell me how far I hit it. Assuming there's no air that day.
How far you hit?
Yeah, how far did I hit it? A great formula for your formula sheet is the projectile formula, by the way.
No, I don't. No, so weird. Do we have the? I don't. Negative 32. Is that negative 32?
That's a good number to have in your formula sheet too. Little g is positive and the formula has a negative in front of it.
Do we need 32 or 32.2?
This is the physics formula.
Whatever you want.
I think it's a good formula only works if you did.
Or like T.
That's not right.
Well, it's the same thing, but the T is not. The T is not inside. It's not inside. Okay. The T is not inside. Oh, that's what the question.
By the way, I know you guys are taking physics at the same time, and you have a physics formula for finding like how far it goes and stuff like that.
Yeah.
That only works if you're hitting it from the ground. The formula you got from physics only works when you hit it from the ground. So take that into consideration if I'm hitting something from a projectile from a height.
I'm not even kidding. It literally works. Yeah, but like it still works out. It still thinks. But it's easy to put out the $10. It's not a bad. So we're doing. So. This is one
How far it went? Is that what you're at?
Yep. Yeah, so make sure you have both types of little g in your formula sheet for Wednesday. Being 32 feet per second squared or 9.8 meters per second squared. Because those will not be given to you. I'm expecting you to have them on your formula sheet. Okay. So 5. I can just take this and make it like 12.5 plus 15t minus 4t squared equals 0, and then deal with that. So then t equals negative b plus or minus the square root of b squared. 15 squared is 225 minus
Oh, you broke.
4 a c all over 2a So make those positive. And then you're gonna go for the positive square root then. And so then pull up our handy dandy calculator. So 225 plus 16 times 12.5. That's equal to 5, take the square root, plus 15, divide that by 8.
Oh, wait.
So then T is 4.452. So then plug that into plug that into the x component of the function, which was 60 times 3 square root. And I get 462 feet. And so 462 feet, 0.6, right? And then if I'm golfing, we usually like to measure golf things in yards, right? So divide that by 3, and that's 154 yards, right? Not too shabby. Okay. Into the x component.
Okay.
That tells you how far. Uh-huh. Question. Yeah, because when it hits the ground, y is 0. Mhm.
What happens if you actually use the X?
If you solve for when x is 0, you'd solve for when that would just give you the starting position. Yep. Okay. Now let's take a little bit simpler projectile function of say like r of t equals say like 4t minus 3 halves 4ti minus let's say like plus 10 minus 3 halves t squared j. So this is similar to like a projectile function, right? Just with simpler numbers. Okay. Now I want us to find capital T and maybe even capital N if we have time. And we can also find the speed, the velocity and speed on our way to getting that, right? Maybe even the acceleration. Yep. So first I want us to find r prime, then the speed, and then t, which is r prime over the speed. Also a good thing to have on your formula sheet.
You get a different T.
No, not like that. Like the mirror,
So RT is 4, R prime T is 4I minus 3TJ, which means that our speed is the square root of 16 plus 9t squared. And so then t is then going to be 4 over the square root of 16 plus 9t squared I minus 3t over the square root of 16 plus 9t squared j. Right? Okay. Now, I want to demonstrate finding n the hard way. 5 minutes or so to go, 6 minutes left in class. I think we can do this. Okay. I'm just going to start doing it up here. Okay. So, if you get one of these, the best thing to do is to write it so that you're doing chain rule or product rule more than quotient rule. So I would write t again as, say, 4 times 16 plus 9t squared to the 1/2 power I minus 3t. I don't need the parentheses there. Minus 3t times 16 minus 9t squared to the negative, no, it's negative 1/2, negative 1/2 j. Okay? So step 1 for finding n, because remember that n is t prime over the magnitude of t prime. Okay? So we got to find t prime. So t prime then is going to be so 4 times negative 1/2 times 16 plus 9t squared to the negative 3/2 times product rule, which would give us 18t I. And then let's do the j term next. So minus, for this one, we need to do the product rule. So we got, we're doing j term, so then 3, the derivative of 3t, the derivative of 3t is just 3. And then times 16 minus 9t squared. And then really it would just, I would just keep it the same. But I'm going to do something here. I'll do it one step at a time. No, I'm just gonna, because of time, I'm gonna do something strange that'll only make sense to you in the fact that I'm finding the common denominator a step ahead of myself. Okay? So I'm gonna find the common denominator a step ahead of myself. Okay? So I'm gonna make this, it would be to the negative 1/2, right? But the negative 1/2 is the same thing as like 1 minus 3/2. So 16 minus 9t squared to the negative 3/2. Okay? What's that? Okay. And so then I was doing product rule. Here's the other half of the product rule is plus 3t times 16 minus 9t. Oh, now I'm doing chain rule. 3t times negative 1/2 times 16 minus 9t squared, the negative 3/2 times 18t, and this j. Sorry about that, running out of space there. Okay, so let's simplify this. So t prime is, I've got a 4 and a negative 1/2 and 18. So that makes it negative 36t. So negative 36t. And then I'm going to start writing it as fractions again. Over 16 plus 9 t squared to the 3/2 power I. Okay. And then we're combining like terms here. So I've got like let me actually rewrite this line before I combine like terms. Because there's so much going on there. So basically, this big kahuna, I can rewrite as negative. I'm going to expand. So 3 times 16 is what, 48? Yes. So 48 minus, yes.
16 minus 9t squared twice in the first place.
I'm finding the common denominator a step ahead of myself. So like I've got a negative 3/2 over here, which is a negative power, means it's in the denominator. I want to combine my terms. Here I would have gotten the chain rule, I would have done this there, so I would have had a negative 1/2. But negative 1/2 is the same as 1 minus 3/2. So I did that to get a common denominator, which is a common thing that happens when you're doing a capital N. Okay? So 3 times 16 is 48. 3 times 9 is negative, so negative 27t squared. And then over here, I've got 18t as a negative 1/2 is negative 9. So then I've got another, wait a second. 1/2. Oh, that's a negative 18. This is no. My positive turned into a negative. Trouble. Trouble. Okay, so it's a positive 27, but then I get over here, I get minus 27 t squared, then times the 16 plus 9 t squared to the negative 3/2. And isn't that nifty? So I'm left with minus 48 over 16 plus 9 t squared to the 3/2 power j. And that's the key for doing these sorts of things, is expecting the simplification, finding common denominators. Okay? Be brave, find the common denominators. Lots of things cancel when you're doing a big N, even though the derivatives look awful. Okay? Now I'll stop here, but once you're here, half the battle's done. Now you just gotta find like the magnitude of the guy. Half powers turn into whole powers, it's all fine and dandy. Okay? And that is a harder problem than you'll see in the exam. So I just wanted to like.
So we know how to do it.
Like here.
In case we
Mark wrong if we just do the flip thing.
Yeah, no,
Draw a picture.
What?
You got a 50-50 shot of being right if you do this. Yep. All right. And then as you guys are leaving, I'm just gonna finish out this problem as you guys leave. And I'll post this, I'm posting it to a couple students who are gone. I'll just leave it for all of you. Okay? Sound good? All right. Yeah. Yeah.
Are we still gonna get like credit or are you gonna?
Draw a picture. You got a 50-50 shot of getting the right answer when you like, because you gotta make one term negative. So like if you do it, but you make a small mistake, there's a lot of like partial credit you're losing.
Okay.
That makes sense?
Don't do it anymore.
Well, I'll give you full credit for the right answer. You're just like, there's a lot of partial credit you're leaving on the table there.
You got it. Can I just do that? It should be fine, right?
Yeah? Okay. All right, so I'm gonna start doing the magnitude of T prime up here and post this video. You can jump to the end of the video to see it, okay? And then, for those of you who have grading questions, feel free to stop by Monday, Tuesday, whenever, to talk about what things were wrong with your homework. Sound good? Okay,
Have a good weekend.
yep.
You said talk to you after class.
Yeah, but I'm gonna start doing this right now.
Okay.
Yeah, okay. Sound good. Okay. So, finding the magnitude of T prime here. I'm going to, one thing to do before you find the magnitude of something like this is if you have a common multiple. So in this case, 36 and 48 have common multiples of 12. That would be nice to kind of pull that out. So it's negative 12. It's 12 times negative 3t over 16 plus 9t squared to the 3 halves I, and then plus 12 times negative 4 over 16 plus 9t squared to 3 halves j. And so then when I find the magnitude of t prime, you can kind of take that factor of 12 and just put it out here and square root everything else. So the negative 3t comes to 9t squared over 16 plus 9t squared cubed, because I squared that term, plus negative 4 squared is 16 over 16 plus 9t squared cubed. And so then that's going to be 12 times square root of basically 16 plus 9t squared over 16 plus 9t squared cubed. Well, that's just going to be 12 times. Notice how like you got these, this is the one that's cubed. So it's like a square root of that, the square root of 1 over 16 plus 9t squared squared. And so square root of something squared, if you know it's going to be positive on the inside, is just going to be 12 over 16 plus 9t squared. Which means we'll take n will be t prime over the magnitude of t prime, which means you can just sort of like take this guy and multiply by its reciprocal. And so if we're multiplying by its reciprocal, we're kind of divide those numerators by 12, and we're going to get negative 3t over the square root of 16 plus 9t squared I minus 4 over the square root of 16 plus 9t squared j. And that's it. That's n right there. So that completes that guy. And I'll end the video here.